good things need time. So, okay, don't. But at least we have started to communicate some ideas, and you are much, not only younger, but also much smarter than I am, so you will take them to profit more than I have. If you will like to do so, because there are many things, many other things that you can consider. And for the exam, I understand it is going to be a multiple choice. Maybe I will prepare tomorrow, but with four or five questions, I will see about definitions of the main few objects. Okay, so that shouldn't bother you too much. Like how a Lyapunov exponent is defined, an invariant probability, just simple things like this. Then today you start, I guess, more with applications with Professor Fataf. So. And maybe it's time to start. Okay, so today we go on with the theory of probabilities for dynamical systems, but then also for what are called stochastic systems, okay? Anyways, first, let me see, this we have already covered. Yeah, okay, so it is time to say something about stochastics. Maybe we can eliminate this whistle here, because, well, it stopped. Okay, so the first thing we need to know is the notion of a random variable. Okay, let me take my iPad, because so I don't tell you something wrong. Because I made notes for myself this morning that you find also in the Dropbox. Huh? This? Okay. Okay. So the first thing we need is to define a random variable. A random variable is basically everything. Can be everything. A random variable is a measurable function, but we don't do anything without measurable functions, okay? What is a measurable function? Actually, I didn't tell you. A function is measurable if it maps measurable sets in measurable sets. What are the measurable sets? The measurable sets are those that belong to the sigma algebra. Okay, so because they are the ones that you have decided they should be measured. Okay, and then a function goes from a certain measurable space, that usually we called it M, to another measurable space, which in these notes is called S. Now, there is a sigma algebra here and there is a sigma algebra here. And the measurable function takes the measurable sets here to the measurable sets here. That's nothing more than that. Okay, for instance, continuous functions are measurable functions. Now, what is a random variable? A random variable is a map between two measurable spaces. In fact, we have to say a little more. We have to say that in the space from which you start, you have a probability. So you need to have a triple, which is M, sigma, the sigma algebra, and P, a probability. Usually we called it mu, but here they call it P. It's the same thing. Okay? Then any function, okay, that goes from M to S that is measurable, and so in S we have to have another sigma algebra, call it sigma. Okay? Any function of that kind is called a random variable. Why do you call it a random variable if it is a function? Because you assume that this function is not known. Okay? It's not known. It is known only with some probability. That's why we need a P. So, for instance, say the result of tossing a coin is a random variable. Because you toss the coin, and you know that you will have head or tail, but you don't know which. Okay? You only have a probability. So this is a random variable. Now, what is a stochastic process? So this is random variable. A stochastic process is a collection of random variables that are indexed by a certain parameter t. Okay? So a stochastic process becomes a collection of variables xt such that t belongs to some set. And we call it t because usually what we mean is something that changes in time. So t stands for time. But it is not necessary, okay? It could be a place somewhere. But the standard thing is to have something that is ordered. So if t is a number, is a real number, then it is ordered. Okay? The smaller number, the numbers to the left come before the numbers to the right, and there is an ordering on the real line. You have an ordering on the integers. So real and integers are usually the most simple sets of parameters, but they could be an interval. You know, in relativity, certain phenomena, I mean, random phenomena in relativity are quite a complex business. And to define them, in fact, one of the complexity comes from the fact that you need this to be, for instance, a 7-dimensional space. Not good. Not good, because that is not ordered. Okay? Like, it's enough you have a 2-dimensional space and there is no ordering. Okay? Does this point come before or after this point? There is no ordering there. Okay? In some sense, there is what is called the partial ordering, but here that doesn't even work. So in any case, for us, and not only for us, but very most commonly, a stochastic process is a collection of these functions. What do we do with this parameter? Well, for instance, we spoke about tossing a coin. Then you can have tossing a coin at time 0, tossing a coin at time 1, tossing a coin at time 2, and so on. Now, the sequence of this tossing becomes a stochastic process. Okay? The temperature that we mentioned various times is a stochastic process because maybe we can reduce this a little because it whistles, it goes beep. The temperature, the moment that you measure it is not random because you measure it, it has a value. Like when you have tossed your coin and then you see it is either head, okay. It is either head or tail. It cannot be both. Or it cannot be head with some probability and tail with another probability. Okay? If it is head, it's head. So it is not random anymore. The same way, temperature now, if I take a thermometer and I measure it, is what it is. Maybe it is known with a finite precision because every measurement tool only gets things with a finite precision. But it is known, so it's not random anymore. But if I want to say what is temperature tomorrow, and then the day after tomorrow, and the day after tomorrow, okay, these constitute a stochastic process. In this sense, temperature becomes a stochastic process. Okay? It is a function. Now, we may know the rule of evolution. In dynamical systems, we know how evolution takes place. Okay? X dot, we said, equals to some g of x. This is a special fortunate case. Although it is very complex. Stochastic processes are easier in general. You can get many more results for stochastic processes thanks to the fact that you already have a probability. While here, probability has to be built. You remember? Huh? I gave you the recipes to build what probability will be at a later time, and so on. Okay? So this is really very brief about random variable and stochastic processes. Now, what do we do with them? Well, they also correspond to an evolution. Huh? If we say that this is time, they also correspond to an evolution. This evolution includes also this. Okay? Only that here you have to do more work. Here part of the work is already done. But there are many cases, as I said at the very beginning of our classes, that we cannot write like this. We cannot write like that because maybe a formula like that doesn't exist. Or simply because maybe we don't know. We don't know that there is a G. If we have to place a camera on a comet, we know G. It has got to do with the law of gravitation. But if we have to speak about investing money on the stock market, well, then forget about knowing this. Okay? There is no chance. So the only possibility, if it exists, is that of a stochastic process. And in fact, stochastic processes have been largely developed in the field of economy and finance. Nobel Prizes have been given to mathematicians and economists that were like mathematicians, an Italian, for instance, or the very famous mathematician from Princeton, who was also a character of a movie, The Beautiful Mind. Okay, mathematician, he got the Nobel Prize for economy. Okay. Well, because he knew how to deal with mathematical models. And the Italian now, it escapes me, he was in Chicago. Well, anyway, he got it precisely for stochastic processes. Now, how can we go about the evolution of a probability in a situation that is so wide and allows everything? Well, something can be done. something can be done, so let's take a look at this something that can be done. Suppose that our probability is absolutely continuous with respect to the volume, the Lebesgue measure on this space M, and so it has a density. Suppose the probability has got a density that I call W in these notes because it is the notation used in various books on stochastic processes. And if you are interested, two good ones are one by Gardiner edited by Springer. Now I don't remember exactly the title, but you search for Gardiner stochastic, you find the book. It's very easy. And the other one is Risken, which focuses more on one way of solving the evolution of a stochastic, the evolution of a probability density under a stochastic process, and which is the Fokker-Planck equation. And I'm going to write the Fokker-Planck equation today, I hope. And in the book, there is the title of the book contains Fokker-Planck. Anyway, these are two. These two books can be recommended. Okay, so we have our probability. We want to see it evolve. So our probability will be defined on Z, where Z is in our space, would be our M. Okay, and we want to know what it will be at a later time. Okay, T is the time where we are, and we want to see what this becomes after a certain interval tau. Okay? How can we get this? Well, we can use some definition, which are tautological. Okay, they don't add any information because they just repeat what we know. But it's always a good idea to start from what we know. You see the eraser somewhere? Huh? Ah, up there, yes, thank you. So we will say this, which becomes a definition of a certain quantity. We will say that this is equal to integral over all possible values Z of what is called a transition probability that takes you from time from Z at time t, that takes you to Z at time t plus tau, because this is what you want to get, starting from somewhere else at t. Z dash at t, okay, times what the probability density was earlier on in Z dash. And then you integrate over all possible starting points. Okay? Now, this is one reflection of what is also called the formula of total probabilities. It is specified in this. What is the probability of going, maybe I do it here. Say you want to be here at time t plus tau. In the stochastic process, maybe you want to have head. Okay, you want to be there, so this is Z. You want to be there at t plus tau. What is the probability of being in Z at t plus tau? Is the sum over all probabilities of having been in other places at time t. This is another Z prime at time t. This is another Z prime at time t. Okay? So you had the probability of being here, being here, or being here. That is given by our probability density times dz at time t. And then you will have a certain probability of going there. And this is our P. Of course, you may have a probability of going somewhere else. Okay? So the meaning of this formula is to sum up all the contributions that go there. This formula does what we have called so far the preimage, in some sense. Okay? Not in some sense, it's like the preimage. This is the preimage. Only that it is not on the sets, it is already on the probability. Okay? Yes?
Tau should also be in the T?
Sorry, what about? Tau, yes. No, this is the time lag. How much later you want to go. You are at time t, and then you want to be a later time there, okay? So tau is another thing that usually you would take larger than 0. It is for a later time, okay? Yes, please stop me anytime, okay? Stop me anytime. Now, we call this transition probability. The meaning is obvious because it gives you the probability of going of transiting from here to here. But it's still a probability, so it has to obey the usual properties of a probability, which is probability of z t plus tau given it was z prime at time. Yeah, this is how you read it, okay? With this vertical bar here, you read it as probability of being in z at time t plus tau given that it was in z prime at time t. It is a probability, so it must be bigger or equal than 0. Moreover, if you integrate over all possibilities, you have to get 1. So, what are all the possibilities? Look, it is integral of p z at time t plus tau, given it was z prime at time t, integrated in all possible outcomes. So, at time t plus tau, you will have to be somewhere. If you consider all possible places where you can go, then you certainly go to one of them. So, this has to be equal to 1. If you want to go to a specific place, it will be something smaller than 1. But if you start at time t and you want, and in z prime, and you go somewhere, you surely go somewhere. It could be even remaining there. Okay? So, say you started from this point, you integrate over all the other points, which include this, and itself, then that must be 1. Okay? Now, these transition probabilities can be quite ugly and complicated if they correspond to a deterministic dynamics, which is dissipative. I don't remember if I told you, but dissipative means that lambda of x, which was our divergence of the vector field G, is negative. Maybe it fluctuates, but then it must be negative on average. Okay? So, for dissipative systems which contract volumes, you remember that the divergence is the contraction rate, is the variation rate. If it is negative, means volume contract. Then the set where you are going to go is ugly. Okay? Ugly in the sense it can be beautiful. The Mandelbrot set is beautiful, but it's hard to handle. Okay, so the mathematics becomes quite complicated. Okay, we will not treat those cases immediately, although many of them can be treated. This is just to tell you that there are some kind of processes that we exclude. Many of this kind can also be included. Okay? So we will say that our process, the stochastic process that corresponds to this evolution of probabilities, is regular. And what does it mean that it is regular? It means that it has some decent continuity property. So what we say, it is regular if limit for the time lag tau gone to 0 of p of z at time t plus tau, given that it was in z prime at time t. So when you approach the initial point, our probability becomes a Dirac delta function. Okay? Which is not a function, you know. It is called function loosely. It is an operator. It is an operator that you can use inside an integral. And then if you multiply by the integration element, it becomes a measure. Okay? This is to say that if the lag time goes down to 0, you have probability 1 of sitting where you started, and probability 0 of being anywhere else. So it's not too bad to require. Okay? In deterministic systems, this will be good for most of the times. Okay? If you have a smooth vector field, then that is going to be true. If the vector field is not smooth, then that is not going to be true in general, because if the field is something like that, okay, and you sit here arbitrarily close to this point of discontinuity, and here, and say you call this z prime, sorry, you call this z, no, this is z prime, okay? And by taking time to 0, you go either like this or either like that. You see that it is not going to be the same, okay? If z prime was here, then when you take the limit, taking the limit doesn't mean evaluating the function on the spot. It means approaching. Well, if you approach this way, you go to a different point. So the field, the vector field, should be decent. Otherwise, this hypothesis doesn't. Unfortunately, discontinuous vector fields are everywhere. Okay? So this gives you an idea of what we are eliminating. I drew for you yesterday one of these discontinuous vector fields, but this is easy to handle because the discontinuities are placed in a countable number of spots, and they can be clearly identified. But if you have a point particle that moves within flat walls, it bounces elastically, it draws a trajectory like this. Well, these are discontinuous points for the vector field because the trajectory in positions space is continuous, but the velocities are discontinuous. And you remember that in our points gamma, okay, we included both positions and momenta, which is also velocities. Okay? So this picture would have a difficulty to be applied here, except that we can identify these discontinuity points, and what happens at them is also clearly identified, so it is a situation we can handle. But a situation that people learned to handle quite recently. Not for you, because you are all very young. Okay, but it was in the 70s of last century, so it makes 70 years ago? No, 50 years ago. 50 years ago. Oh, it's a sizable time, but it's not much for me. Okay, so we will have this kind of processes, regular ones. Okay? Now, because you have a probability, probably you know, but I didn't tell you, with a probability you can compute not only averages, expected values, but you can compute the properties that are called moments. Moments are important, are very important to characterize the probability. So I call Mn of a certain variable x, the integral over the whole space, so I don't write here because I didn't specify the space, of x to the n, we used to call it mu, but now to use the stochastic notation, I call it p. Okay, it is the p that I have here. So this is an average. It is an expected value. Okay, it is the expected value of x raised to the n power. Okay? So we have a probability, although it is a special kind, it is a transition probability, but it will have its own moments. Okay, these are called moments. How many of you have already heard about this notion? You know. Anyways, that is the definition. Okay? Nothing mysterious, although it has a lot of consequence. So this is moment, nth moment. So also the transition probability has got moments. And let's call it Mn. Okay, Mn, Z prime, T and tau. Okay, we take it function of the three variables. The starting point, the starting time, and the lag time. Okay, that is equal to integral. Now, in my notes, I decided to consider a one-dimensional process. Okay, so this x takes value in the real line. So here I write an integral from minus infinity to infinity, but in my notes. But you don't need to. Okay, but let's make it simple, like in my notes. So let's say that xt goes from my space M to the real numbers. Okay? Then here I can integrate over all numbers from minus infinity to infinity of this quantity, z minus z prime, raised to the nth power, p of z at time t plus tau, given that it was in z prime at time t, dz. Okay? So this is the nth moment with respect to z prime of the probability p, of the transition probability p. I have integrated over z, so it remains dependent on the other parameters. Now, a function that is exceedingly useful in dealing with probabilities is what is called characteristic function. Now, you remember that I called characteristic function the function of a set that is 1 when you lie in the set is 0 when you are outside the set. I told you this is the language used by analysts. Probabilists call it indicator function. Well, because for them the characteristic function is what I'm going to write now. Okay? It is something totally different. So let us introduce the characteristic function. C, of course, for characteristic, is a function of u. You will recognize what it is in a moment. Z prime, t and tau. And is defined like this. It is a Fourier transform. Okay? It is the integral from minus infinity to infinity of e to the I u z minus z prime probability of being in z at time t plus tau, given that you were in z prime at time t, dz. Okay? So it is a Fourier transform with respect to the variable z that then in its Fourier space it gets replaced by the variable u. Now this function, it can be proven. It's not even particularly difficult. You have to expand the exponential. You know that the expansion of exponential exists, so you are safe. You expand the exponential as a Taylor series, you get powers. And the powers will be these ones, plus coefficients. So you see that the characteristic function is related to the moments through an expansion. And in fact, this will be equal to 1 because the integral of 1 with a probability is 1. It is its definition here. If I multiply by 1, nothing changes and I get 1. So first term is 1, and then there is a sum that goes from 1 to infinity of I u to the n divided by n factorial times the moments mn of z prime t and tau. Okay? Now look, you recognize the moment. Okay? It is what is left. Once you have taken away IU to the n. Now, what have we done so far? Basically nothing. Okay? We have only introduced objects that depend on an unknown object, and therefore they themselves are unknown. But we have prepared the stage for more that we will see in a minute. But you should excuse me a second. I come back soon. Okay? Just give me 1 minute. This maybe doesn't come with me. So, yes, we have done nothing, but we set the stage. Let me recap. We have a process. It is called stochastic because it is known only through probabilities of what will happen. Unlike the function y equals x squared, that is not known with probability. Ooh, thank you. Okay, if I write y equals x squared, that is known with certainty. You give me 1 and you get 1. You give me 5 and you get 25. This can nevertheless be included within a stochastic process where the probability is 1 for the right values, those that have this form, and is 0 for all the others. So the framework is very wide. But in general, it happens that you don't know what it is. So so the probability is something more complex. And this probability can change in time. And if we are lucky, the probability has got a density. And now we are in the case in which the probability has got a density. Now, the reasoning goes this way. There is a density that changes in time. We don't know so far how it changes, but if it changes, there will be some transition probability that makes it change. So I don't know this, but I know that it exists. I don't know this, but I know that it exists. So this equality here becomes the definition of the transition probability. Okay? Now you tell me you know nothing about it. True, because I know nothing about this and I know nothing about that. But because I know that this exists and this exists, how do I know? I have assumed it. I'm in the framework in which it exists. Because I know that they exist, then this must exist. So this is the definition of P. Once I have defined the P, because it is a probability, it has to have these two properties. It cannot be negative, and its integral must give you 1. Well then, somehow, okay, it will have moments. And this is an extra property that we have required to make the calculations that now you will see I'm going to do. Okay? So we have done nothing. We have gone from unknown to unknown. But let's see if we can go beyond. And we can do it after we have introduced the characteristic function. Okay? After we have introduced the characteristic function, we can write the following. We can say that because this is a Fourier transform, if we are in a world where things are regular, and all these also regularity properties are satisfied, then like P has a Fourier transform, the characteristic function has its own Fourier transform, which is the anti-transform that takes you back. Okay? So we can say that P of Z at time t plus tau, given that it was Z prime at time t, is equal to, now this is the anti-Fourier transform in one dimension, 1 over 2 pi integral from minus infinity to infinity of E2 minus IU. You see the difference between transform and anti-transform basically is that here you have a plus, and here you have a minus. This factor 1 over 2 pi that is missing here is conventional. So mathematicians prefer to see things in a symmetric fashion, and they would define the transform as 1 over root of 2 pi integral from minus infinity to infinity e to the IU whatever. And then the anti-transform as 1 over root of 2 pi integral from minus infinity to infinity of e to minus IU whatever. So this becomes symmetric. Okay? And transform and anti-transform constitute together an involution. Something that you apply twice and you get back where you started. It's unitary transformation. Written in this way. Physicists and engineers in applications, for reasons related to their work, they prefer this other convention, that the transform has no division by 2 pi, and the anti-transform has division by 2 pi. So the root 2 pi gets cumulated in here. It is the same thing. It's only convention. Okay? Of course, quantitatively, you get the difference. But the calculations go along exactly the same. So now, this, okay, the anti-transform of the C takes me back to that. Okay? So it is 1 over 2 pi e to minus u z minus z prime of the function C, the characteristic function that depends on u. What is the order? U, z prime, t, and tau, which I have just defined. And this will be integrated with respect to the Fourier variable, which is u. Okay? This removes u and gives you back the z. But for the characteristic function, we have written this expansion. So this can also be written as, let's see if I can fit it, maybe better go below, 1 over 2 pi integral from minus infinity to infinity of e to minus IU z minus z prime of the expansion, which is 1 plus sum in n from 1 to infinity of IU raised to the n power divided by n factorial times the moments mn of z prime t and tau, all this within brackets integrated in du. Okay? All these things are unknown so far, but they are what they are. Okay? All these things, given our definitions, are perfectly legitimate. But now look carefully. Look carefully what we get. We are going to get an equation for the evolution of the probability density. Now, the probability density is unknown, but I will have a rule to compute it if you give me the initial condition. Okay? So, let me see if I have time to write this. Yeah, because we have little less than 15 minutes. So, I should be able to do it. So, what is the product that we have in this integral? Have a question? Please, please. What?
Because there is t.
I know, but we started a bit late. Do you want to go to tea? I finish on Friday then. I stop here and I finish on Friday. Okay, let's go to tea. Let's go to tea. I stop. Yeah, because we started late, but it's not their fault. Then the tea gets cold. Okay, I see you on Friday. Have a good day. Yes.
We call it moment, like these.
Moment. And that honestly, I don't know.
Somewhere I know, I read there's some concept related to moment of inertia, and they are saying that okay, we are trying to see how your data is deviating from the mean or something. Is it true or
No. Okay.